Evening, dear participant, and welcome in this session. Today we are going to cover the topic associated with the Matlab solvers. These solvers are based on some numerical methods, and we can apply these solvers ordinary differential equations and also in partial differential equations. But there are numerous solvers which has been developed for the different type of methods by using numerical methods and other some new techniques also, which are very helpful to find out some complex problems in the partial differential equations as well as ordinary differential equations. And these methods are very helpful to find out numerical results and reduce the complexity in the calculations. There are numerous problems which we are not able to find out the solutions analytically, but these approaches numerically always help us, and when we need to establish some mathematical model and graphical interpretations, in that particular case, these methods are always help us in many ways. Today, some participants are with us. Okay, Vani, Madhvi, good evening. And first of all, I would like to share my screen, which is, I hope, visible to all of you. My screen is visible. Okay. Yeah. Obenga, good evening. I think you are from Nigeria and you are always with a part of these sessions. Yes. I know my screen is visible to all of you, and this is the presentation. And yes, so the topic Matlab solvers for ordinary differential equations based initial problems, whether it is a stiff problem and non-stiff. So both type of problems we can solve by using these techniques, and I hope this content will be really very helpful for all of you in many ways. Okay, so here this is the main agenda. First, we will discuss about the numerical methods for ordinary differential equations. Then we will solve initial value problems using MATLAB built-in functions, and all these MATLAB built-in functions are the solvers. We will discuss in detail about this. Okay. Then by using the same, we have three examples are presented by using the solvers for one initial condition. And in case number third, we have the 2 points boundary value problem for the second order differential equation. And one example has been presented, how we can reduce the order of differential equations. And then one example is presented here. But the thing is, all the participants, I request you to keep in touch throughout the session, because in the beginning, I will explain about the solvers, and last example is important because of we have a second order differential equation, and sometimes it may be third order or fourth order, and accordingly we are given the boundary conditions. But we need to reduce the order of the differential equation to the first order. Only then we will be able to solve this type of problems. But the thing is, in this fourth example, we have only second order differential equation, but the content, the topic which we are covering in this session will be very helpful for all of you in the for the ODE as well as PDE. But this is the basic introduction about the MATLAB and built solvers. Okay, so here is the numerical method for ordinary differential equation. Sometimes when we have please let me know if there is internet issue for all the participants, or only one participant have the internet issue. So I can check it. Please reply in the chat box immediately so that I can remove the problem if the problem is from me side. It seems to me the problem is from me side. One is saying internet issue. I ask from the other participant if you have the same issue. Please let me know. Okay, so I am going ahead. Okay, just 1 minute. I am checking it if the problem is from my side. Please give me 1 minute. Okay. Okay. Now it seems to be fine from his side, and you are getting all the things. Yes, it is working now. So the thing is, we were talking about the first order differential equation, and in general problem, more general problems as formulated as follow. If we have the higher order is involving in our the given differential equation. So f is a function of n variable. What happened? Okay. Okay. So no problem. Yes. So I was at his place. Control Shift 1. Control Shift and 1. So here you can see more general problem formulated. If we have y is equal to yt, and that satisfies the nth order differential equation in this form. Yn is equal to, we have FTY example will be okay. So we discuss all the problems associated with this type of problems. Here you can see some MATLAB solvers. So MATLAB has the several functions for computing numerical solutions of the initial value problems of ordinary differential equations, and these are the listed some solvers. You can see ODE 23. This method And that's why with the combination of this Runge-Kutta 2-3 order, we have ODE 2-3 method. Similarly, we have ODE 45. This also is used for non-stiff type of problems, and the method is based on Runge-Kutta 4-5 order. Okay, so explicit Runge-Kutta 4-5 formula is used to establish this solver. Okay, so all these solvers are based on some numerical methods which we have studied in numerical methods. Okay. Similarly, we have ODE 113. This is also used for the non-stiff type of differential equations, and this method is based on Adams-Bashforth-Moulton solver. Okay, by using this approach, we have ODE 113, and also you can see this method was used in the last session. ODE 15S. This method is used for the stiff type of differential equations, and this method is based on the numerical differentiation formula. And the last one you can see here is ODE 23S. They do not required to write the complete program for these methods. Just we need to understand the syntax, how we can use these solvers for the differential equations with the initial conditions are given. Okay, see here, this is the syntax, simplest form, which with the t-span, and t-span mean interval, and this will be the initial condition. So these are some parts of when we wanted to find out the solution. T is t and y. These are the t is the independent variable and y will be dependent variable. Okay, so this will return the solution for t and y. Okay. Fun is the string which contains the name of the ODE, and we will save the file which will be M file. Okay, that describes the differential equations. T-span is the interval of the integration. Y naught is the vector holding the initial conditions value. If T-span, notice point, if T-span has more than 2 elements, then solvers returns computed value of y at this point. When we are given one, we will use for the initial value, and other will return the value of y function at the other point. So the output parameters t and y are the vectors holding the point of the evaluation, and computed values of y at this point. Okay, and next we have this is the very simple example for y at this point. T is equal to 0, 0.25, 0.5, 0.75, and 1. So we have the interval from 0 to 1. At this point we want to calculate the values, and we have this very simple example at this place. First order y dash is equal to minus 2ty square. Okay, with this is the initial condition. So is this part nothing but only we have this differential equation at this place. So we will write the differential equation as a function. Okay, note this point again. First step is we need to write a script file as a function of a differential equation. Only for this equation. Okay, only for this one. So function we have dy. This is equation number 1, and this differential equation is involving 2 variables t and y. Okay, and equal to, we have minus 2 dot cap 2. Okay, so this is the, okay, so we can write this above equation in this way. Now we want to compute this equation with both the methods. So a1 y1 is the value of t, and first solution by using ODE 23. See this statement very carefully. We have the syntax like in this way: solver, then we have fun, this is the function, okay, this is the function, then t-span, and then the condition. Okay, so at this place you can see we have the equation. This equation will be called at this place, which we have created in this script file. Okay, note this point. This is the separate script file, and this is the above part is the necessary to understand. So here we are using the syntax. This is the solver, this is the equation 1. Okay, this function is used at this place. So the function which we create for the differential equation will be used automatically at this place. Then we have the t-span, and the t-span we have is at this place. This first solver, which is ODE 23. Then by using the same differential equation, we are using the another ODE 45, sorry. So t2 and y2, these are the values of t and y. Okay, so y1 is used for first solution, y2 is used for second solution. Okay, so t1 and t2 will remain same for both the equations, but we are giving separate name, doesn't matter. And rest syntax which are same. Here we have equation number 1, we have t-span, and these parts will remain same is for ODE 23 as well as ODE 45. Okay, so sorry if I have you are facing some network issue today, and later you can see after the lecture also, and I will try to finish this lecture, today's session, as soon as possible. Okay, so first we need to check in the MATLAB. Come to in the MATLAB. Yes, we have to, yes, this is the first example. This is the first example. I am closing all these files. Yes. So what you will do, see in the MATLAB, this is the same differential equation, okay, which was given to us, and we write a function. You need to save this file in your MATLAB. Okay, so here from this place we are given y dash is equal to minus 2ty square. Okay, the first part, see only the first part from the function and dy1. So this part is the MATLAB function in the form of differential equation, and we save, you need to save this file with the equation number 1. Okay, you can give any name, but the thing is, while you are calling the function, because now this is a function but for differential equation, so this function will be saved at this place. The name of the function at this place and the name of the file must be same. Okay, now we will call this differential equation at this place. So this is very beautiful script file which you can see. CLC and clear we use for clear the command window and clear all the variables which are saved in the workspace. Format we are using here long format, and then you can see the next statement, T spent. This is the same as we explained in the presentation. This is the next statement for ODE 2-3, and this is for the ODE 4-5. So when you will execute these sequence of statement, you will have the solutions, but you need these solutions to compare in tabular form. So to get the results in tabular form, you will use this statement. So a solution is equal to T1. You can use either T1 or T2 because T1 and T2 have the same values. I am using here T1, and the second 2, 3, and Y2 will be the solution of the same differential equation using the solver ODE 4-5. Okay, so here we have Y1 and sorry. Yes, so here you have Y1 and at this place you have Y2. When we will execute this sequence of statement, see, we have the numerical results for both the solvers. Yes, so here you can see easily there are 3 columns. First column is the value of T. You can see these values. Okay, and the second column starting from this one and these values. These are the values of Y2. Okay, and this is the last column. Sorry, these are the values for Y1 and these are the values for Y2. Okay, so the solution or the numerical results which we are getting in the command window are in this format, but as you can click in the workspace. When you will click the workspace and you can see the values, these are 5/3. Double click on it. When you will double click on it, you will have the same values at this place. Yes. So first column is T. Second column we have these are the values of Y1, and third column these are the values of Y2. Okay, and this column these are the values of Y by using ODE 2-3, and these are the values for the same differential equation by using ODE 4-5. But here you can, when you will compare these values, you can say that these values for when we have T equal to 0, but when you are using the long format, see this value and this value. Okay, so when you will compare these values, these digit and these digits are not same. Up to 4 decimal places, the values are same, but beyond that, these are not same. There is a very small difference between the results. Okay, and also you can compare at this place. These are these values and differences. There is also difference. Okay, so these are approximate solutions of the differential equation, but not the exact solution. Okay, so depends upon which solver is more suitable for our problem, and according to that we can use the solver to find out the solution of the given differential equation. Okay, so now here is, yes, the same solution which you see in the MATLAB are compared at this place. Here we have one more interesting example, and in this example you can see of the differential equations of first order. So here we have uh, this is y1, and these are system of equations. Okay, and y1 dash is equal to, we have y1t minus 4 y2t, and in the second equation we have y2 dash is equal to minus y1 plus y2, and these are the initial conditions when we have t equal to 0, y1 is equal to 1, and y2 is equal to 0 when we have t is 0. So for this example, we can easily write the ODE M file, but we will not write here the differential equation functions. Okay, because here the problem is that y1 and y2 both these two equations, equation number 1 and equation number 2, both the equations are involving both the variables. So that's why the problem use inline function. There are several ways to write the functions which has been discussed in the previous lectures, and also how we can solve the system of equations, algebraic equations, linear and non-linear equations. So these lectures are very important to study this type of problems, numerical approach when we are using to find out the solutions of differential equations. So the previous lectures are very important to understand this content which we are presenting here, and function. This is inline function. So here you can see from very first equation, we need the coefficient of y1 and y2. Okay, so the coefficient of y1 is 1 and coefficient of y2 is minus 4. Okay, here is minus 4. Okay, make it correct. See this point carefully. This is the coefficient of y1, this is the coefficient of y2 from this equation. Okay, then use a semicolon, and these are the coefficient of the second equation. Coefficient of y1 is minus. Okay, so this is, we have matrix. This is matrix like in this way: 1, 4, minus 1 and 1, and this will include y1 and y2. So when you will multiply these two matrices, you will get the right hand side. Okay, and here is an independent variable and y is dependent variable. So always use independent variable first, then dependent variable. When you will execute this statement, this will return this value. Dy will be equal to dy t comma y is equal to this one. Okay, now after that you can, for the numerical solutions is computed and the initial value are stored is t span and y naught respectively. So t span will be equal to, these are the conditions when we have t is equal to 0. So y1 is interval we have is from 0 to 1. Interval is for 0 to 1, and y naught is equal to, these are the conditions when we have t is equal to 0, y1 is 1 and y2 is equal to 0. These conditions are given in our statement. So here now for the numerical solution of this system, once again if you want to check, you can check here. Yes. Yes, see here. So you can see these are the conditions. Check all these part. This is the condition. Okay, is equal to 0. We have y1 is equal to 1, sorry, y1 is equal to 1 and y2 at 0 is 0. Okay, so here we are using a t-span. T-span we will take at its place for t is equal to 0 to 1. We want to solve the equation for this t-span. Okay, so come here. Yes. Here we are using ODE 23. dy function will be used at this place. There is no difference. In the previous example, we create a function file. Here we are using dy, line function. Okay, and this is the t-span and this is the condition. So these arguments will pass through this solver, and then after this you can see y1 and y2 both depends upon t. So here note this point very carefully. T is the input argument and y depends upon t. So as we have all the values for t-span will pass through this y function, very first solution. Okay, double colon comma 1. 1 is used for the first equation and double colon is used for all the input values, input arguments of t. Okay, if you are not getting understanding about this one, you must read about algebraic solutions. You must read about matrices, their manipulations. Matrices play very important role to help in the understanding of this type of problems, because without matrices we are not able to understand how we are using the results, their manipulations, many more things are there. Okay, so similarly we have this part is used for the y2. Y2 is also depends upon t. Okay, and this is the marker for the graph of second variable y2, and you know help us to recognize the graphs. So y1 will represent the first graph of y1 and this will represent for second graph. So this will help us to understand the when we have the plot of this solution, and y label we are using yt, and title we have numerical solution for y1 and y2. The whole script which we discuss here, see in the MATLAB. See here. Yes. So this is the second example. And in the second example, we have single file. Okay. So these are the given statement here as usual. This is the inline function here. Okay. Then this is we are given span, and these are the conditions for y1 and y2 when t is equal to 0. Okay. Then we are using ODE 23, dy, t-span, y0. These are same syntax. Okay. The green text which you see are not the part of this program. Just these are the instructions and the description about the statements. Okay. Then after we have the plot command and legend for y1, y2, x label is there, y label is there, title is there, and also one more statement we use at its place, grid on. When we will execute all these statements, just you need to run this file, press it run. So you can see you have the graph of the solutions of the results, and this is the legend. This box you can see y1 and y2. y1 graph is in blue color, and y2 the solution of the second variable, second function y2 we have in red color. So these are two solutions of the system of differential equations involving two functions and one variable. If you have any question related to this, you can ask from me. You can put your question in the chat box. And also see here, there are some more statements are there. See, sometimes we need numerical results. So for the numerical result, what we are doing, y1 is equal to y colon 1. So this function will be stored in y2. So here this statement at the end, we want the solution of these two equations in the tabular form along with the t span. Okay, so in single numerical results, okay, I have assigned the assignment for this. Now what will be, when we have the numerical results, all these will be stored in this assignment. See, run this file. Yes, and you can see we have the graph of the solutions as well. Here is this variable. So all the solutions for y1 and y2 can print here. Give the command in command window, numerical results. Okay, so when you have the numerical values in the command window. Okay, and also the another way, you can remove this semicolon. So when you will remove semicolon, you will have the result in the command window. Yes, so the first column is t-span, second column is y1, and third column is y2. And also you can check all these values. Double click at this place. You need to click, double click here. When you will double click, new Excel file will open, and you can check all these values here. So this is t-span, this is y1, this is y2. Okay. So I think these are very, or you want to ask, please you can put your question in the chat box. And also at the end, I will share this script file, this presentation in the WhatsApp group. Okay. Yes. So this has been discussed. Okay. So now here, okay, y1 and y2. Here is one more example. This is the third example. And this example deal with the stiff type of ordinary differential equations. And we have the equation is, you can see the equation is, yes. So this is the differential equation, which is y dash t is equal to minus 1000 into y minus log 1 plus t, plus we have 1 upon 1 plus t, and this is the initial condition. With inline function also, and you can see here dy inline function. So from this place to this place, this is only we have this part. Only this part is at this place. So here you can see minus 1000 product y. Here is minus 1, please correct it. Here is minus 1. Otherwise, this file will not work for you if you will not correct it. Then we have log 1 plus t, and here is plus, then 1 upon 1 plus t. Okay, so this is the function, this one. Then we have t and y as we do in the previous example, and we will use here ODE 23s function on the interval. T span is 0 to 0.5. Okay, so this is the T span we are using here, 0 to 0.5. You can change, you can choose 0 to 1. It's up to you which interval you want to choose. Okay, so the thing is the statement is same as we do in the previous example. Ty ODE 23s and dy is there, t span is there, and this is the condition which we are given here, y naught. This is the value of y naught. Okay, so to illustrate the effect of the stiffness of the differential equation in the equation, we need to plot the graph for the compute differential equation, and the statements are very quite simple. When you will execute this statement, you will have the solution, and the values will be stored at this element. There will be two vectors, one is for t and other is for y. So both the values will be stored at this place. Okay, and we can simply use these to plot the graph. Okay, plot ty. So this statement will plot the results which we get after applying this ODE 23s. Now after that you can manage the axes. Okay, so this is axis for 5 minus 0.05 to 0.55, and this is for the vertical. This is the domain for x, this is for y. Okay, and x label is t, y label is yt, and this is the title. These are the usual statements which we need, which are required to use in the graph. Okay, so now when we will execute all these statements, and which are very simple to use, I think, and you are getting everything. Okay, see in the Matlab. I have to open the next example, and the example I have is, yes, see. So all the statements are in the single file. We need not require it. Okay, Salahuddin asking about how to get the T span. T span is just the solution for the when we want to plot the graph. See once again. See here. See here. We have this is the interval from 0 to 1. Okay. 0 to 1 on the horizontal line, you can see 0 to 1. So T span means the interval for t. Okay, so the initial value we are given is t is equal to 0, and in which find out the solution for the given differential equation. So the one value we are given on the basis of initial value, and the next value you can take either you can we choose for this example, we choose t span for 0 to 1. Okay, you can take at its place 0 to 0.5, you can choose 0 to 2, this depends upon you, but this is the initial condition which is given to us. Okay, now see here, these are the same statement. Once again, sorry, this is the, yes, so the statements which you can see which we are using at this place. So this is the first statement, this is the t span, this is ty, and these are the statement. All these will be used in MATLAB. Okay, so CLC and clear, you know, this is the first statement, then we have t span, then we have the ODE 2, 3, and solution of this equation will be stored in this variable t and y. Then we have the plot statement, plot ty. These are the axes which we fix here. X label and y label you can assign, and at the end we have the title. When you will execute all these sequence of statement, okay, so see, this is the solution. Okay, so this is the stiffness. You can see at this point there is immediate or frequent change in the graph, minus 0.520. The graph is decreasing, and after that immediately it goes to up. Okay, so this point which you can see here is stiffness in the differential equation. Okay, so if you can insert here some more statement, you can use here grid on. The t span, this is minus 0.052 minus 0.052 0.5. Okay, and on the vertical line you can see the range for the graph is minus, I think it will be 0.52, and x label, y label are the same statement as we use usually. I think you got it. Santosh Kumar. Good evening, all of you. Good evening to you also. Today you got late to join today's session. Okay. So now we have the next example. Here is, okay. Yes. So this in this part which we are going to discuss now, this is not easy, but the thing is you need some basic concepts also which we discussed in the previous lectures, because matrices and inverse matrices, how we can solve the system of equations, many things are there, areas of axis. Okay, you can see in the MATLAB, see here, I am changing these values. If I am changing from, suppose it is 0, see the change in the graph. The horizontal line is we have minus 1 to 1. Okay, so that's why our graph in this plot we have only up to 0.5 or 0.6. Okay, so what we do here, we need to manage the axis. Here I am choosing point 0, 5, and here I have, okay, yes. So in this way you can manage the axis, and on the vertical you can see, on the vertical, so these values line, okay. So here, if you are using 2 and this is 0, see. So some part above 1 we don't have the graph, the values we don't have, or the t-span corresponding to the t-span we have only this part of the graph, okay. And if you want to choose some more part below the 0, you can do. Here we need to choose minus 0.05, enough. So in this way you can manage the axis for your you got your answer. So now we have one more example which we are discussing here. Yes, see this part. In this differential equation, we have 2 boundary values, and the differential equation is of a second order. We have second order differential equation, and 2 values are given. Ya is equal to Ya and Yb is equal to Yb. These 2 values, 2 points are given, like we have this interval. Okay, at this point and at this point we are given. If you have, suppose this is the graph, so these values are given. This is the A point, this is the B point. Ya is at its place and Yb at its place. These points are given. So in this case, how we can find out the solution? So the method in the question is that finite difference method. So finite difference method is a technique which I think you have studied in the numerical methods. Okay, so this method is completely based on this, and but here we are dealing with the computing part. So I am not able to expand the complete finite difference method. First you need to study about the same, but here we will explain about the steps which are involving to find out the solution of this type of problem, and you need to create a function to reduce the order of a differential equation. So here the second order we will reduce to first order, and see the complete procedure. Okay, so for that we assume that f is a function in this form, g naught t, g1t and g2t y dash. Here is y and here is y1. Then this is g1t and this is g2t, but here y and y dash are involving here. Thus the function f is linear in both y and y dash, and using the standard second order approximation for y and dash and y double dash, one can easily construct a linear system of equations for computing approximate values of the function, and on the set of evenly spaced point. So the function we will use here boundary value prompts to ODE. This method, and for more detail you can check in the numerical methods how we can reduce the orders for the boundary value prompts. if we are given second order differential equation, then how we can reduce in the first order. Okay, only then, because we have the two boundary value problems, and this must be reduced. Only then we are able to write the program, or we can understand the program which we have created at this place. Okay, otherwise you will face some problems. Okay, see here. Yes, the program is long as compared to the previous examples, and we have to create, yes, this is the first file. So this is the complete program to convert boundary value problems into ODE. Okay, because here we are given the value at the initial point and value at the terminal point. Okay, so that's why first we need to solve the boundary value problem to ODE, and equation we have G naught, G1, G2. Here is G naught, G1, G2, and also we have T span, and the BC is used for the boundary conditions which we are given at this place, this interval. Yes, we are given this interval AB, and we need to divide this interval for the partition of the interval, and we have n plus 2 evenly spaced points T in the interval AB. Okay, so these points will be taken, and G naught, G1, G2 are the string functions respectively which are used at this place. Okay, and the boundary values will be stored in this at this place BC. This is the YA, this is the YB. You can see YA and YB. These two both values will be stored in BC, and BC is used at this place. T span is used at this place, and G naught, G1, G2, you can see all the arguments which are required for our boundary value problem to ODE. Okay, so first we need to create this function, and after creating this algorithm, we can solve this type of problems for the second order boundary value problems. Okay, so by using this algo which we created at this place, you can solve all type of problems by using this one. From 0 to 1, then this is T span 1, this is T span 2, and this is the T span. Okay, so this is the index for this value, and this is the index for the next value. Then we need the line space. Okay, line space, by using the line space we can divide the interval. We have A to B and n plus 2. So these number of points will be created in this interval by using this statement. And T1 is moving from, is the interval from 2 to n plus 1. Okay, so the points will be generated at this place for T1. Now 0 are here, suppose 0.1, then we have 0.02, and so on. We have 0.99. Okay, in this way. So this is the index 1, this is index 2, 3, and this is the index n plus 2. Okay, but we need n plus 1. N plus 1 will be this one. So these are the index. Okay, this value we are given, this value also we are given, but we need to calculate these values. So here we have 2 to n plus 1. These values will be calculated at this place. Now for these values, we need to calculate the value of G naught, value of G1, value of G. After solving these values, we need to store in some variable or the assignment. We are using U1, U, V and W. So after getting the values of all these functions which are coefficient from the differential equation will be stored in U, V, W. After that we will calculate the value of H, which is the increment or the difference between two consecutive points. That is given by this formula. H is equal to B minus A divided by n plus 1. Then we will calculate D1, D2. Okay. So these values will be calculated. Okay. So here is the sum approach, D1, D2, D3, these are the diagonal values. These values are taken from the diagonalization of the approach to reduce the order of the differential equations. Okay, so these steps you can understand only if you have studied this method, finite difference method. Okay, so there are some equations, and from that place we will calculate the values of D1, D2, D3 to get the matrix, and from this we will have the diagonal elements. Okay, we need to diagonalize. So A matrix, this is the A matrix, and from the given values we can get the diagonal D1 minus 1, this is the left, and then we have the diagonal D2, this is the middle, then we have the diagonal D3, this is the right matrix. So this is the just matrix, and then we will create the zeros from n to 1. Now we have the formula for F1 and Fn. F1 is used for the first value left end point, and Fn is used for the right end point. Okay, so these equations we can get from the finite difference method. From that place we are taking we take these two equations. Okay, but here due to lack of time I was not able to create the file for the finite difference method because it will take more time code. Okay, you can easily get the finite difference method from any numerical method, and you need to go through the method, then you can easily understand these equations. Okay, and after that S will be equal to A divided F. Now we are able to find out the solution. So Y is an vector. In first column we have BC1. BC1 will give us the values in the first column according to the given boundary condition, and this is the right end of the interval, and S is given from this place. Okay, and T transpose, because this is the vector and this is also the vector, we need T is equal to T transpose. So this is the complete script file to convert boundary value problems into ordinary differential equations condition. Okay, now see here, we have a very interesting example. Now what we are doing here, by using the boundary value problem to ODE, we want to solve this differential equation. Now this equation is similar to the program which just now discussed here. So that program you can use anywhere for this type of problems. Okay, when you have second order differential equation with the boundary conditions, like in this way, you can easily use the same. Okay, see here. Now here you need to compare this differential equation with G naught T, then G1T, Y, then T2. And these are the conditions. Okay, so now come to the MATLAB, how you can use all these statements in the MATLAB to solve the solution. Now we have the equation, we have the initial conditions. Okay, so CLC and clear are the usual. Now how we can get G naught? G naught is we have this value 1, only 1 is there. So we will use the inline function and we will get the value for the vector t. Okay, t vector will vary from 0 to see here. So the thing is t is if we have from 0 to 1. Okay, so the thing is there are some points 0, 0.1, 0.2 and so on, 0.9, then we have 1. So at each point we have 1. Okay, so we need to generate this. At this place 1 we have 1, 1, 1 and 1. Okay, so we need 2 vectors having the same length, otherwise this statement will not work, because this MATLAB completely based on the matrices, and when we are operating on matrices, and if we want to multiply one array with the other array, this will be possible only if the length of the arrays are equal, because there is element by element multiplication, there is element by element division, there is element by element addition and subtraction. So we need G naught, the vector, and the length must be equal to this one. Similarly, we have this is the G1, okay, and inline sin t. Similarly, we have cos t inline, okay. So G naught, G1, G2, you can see at this place, and all these will be used in ty. Here we are using boundary value problem 2 ODE, which we create a script file. This is the program, and this program you can use anywhere for this type of problems. Now you need to pass this value G naught, G1, G2. This is T span. Okay, then we have the conditions. Both conditions are 1. This is BC. Sorry, this is BC. Yes, and this is the value of n. N is equal to, we have 100. Okay. So when you will execute, we will return the values of t and y. Okay, t will be one vector, one differential equation. Okay, and the solution we will be stored at this place. By using plot statement, we can plot the graph, and these are the axes as we discussed in the previous example. Then we have the time you will execute. When you will execute all these statement in the MATLAB, please wait. I can see there are some questions, and I will try to give you the answer. Okay. So here, when you will execute this statement, we have the solution of the differential equation. You can get the solution of the differential equations at its place. Okay. Yes. I am not getting questions. I think there is again network issue. Okay. So can I? Okay. YouTube is not getting enough data.